Hey everyone, in this video I'm going to talk about randomized controlled trials. And what we mean by that is basically experimental research that examines how a treatment causally affects an outcome by assigning varying values of the treatment variable of the intervention to different observations randomly, and ultimately then measuring their corresponding values of the outcome variable. Right? So randomized controlled trials are kind of the gold standard for causal inference. And we'll go through the logic of why that is and why they're so powerful to help us make causal inferences. The key idea behind randomized controlled trials is that the randomization of the treatment makes the treatment on control groups identical on average, right? So, and we'll talk in a second exactly what we mean by being identical on average, right? Um, but ultimately, kind of to give you an intuition, the treatment and control groups under complete randomization or perfect randomization are ultimately on average similar in terms of all both observed and unobserved characteristics, on average, because they are randomly allocated to the treatment or the control group, so that the only difference between those two groups is the actual treatment status itself, right? And if that is the case, then we can attribute the average difference in the outcome to the difference in the treatment, to the presence or absence of the manipulation or intervention itself. Okay. So now I want to go through this a little bit more formally, a little bit more formally than the book treats this as well, and but it's important to kind of get the underlying mathematical notation kind of right to get a better idea of or get a better conceptual understanding of what is ultimately going on. Okay, so under random assignment, what we ultimately have is that the potential outcomes yi0, so that's the potential outcome for each individual observation under the absence of the treatment, so in the control group, as well as yi1, so the potential outcome in the treatment group for each observation, as well as any additional observed characteristic, are all independent. So this sign denotes statistical independence of the treatment status. So Ti. If the potential outcomes, as well as any other observable characteristics, are independent of the treatment status Ti, that has a couple of important implications. Here we're looking at the conditional expectation. So the expected value of our potential outcome in the treatment group, conditional on the treatment assignment being or conditional on the treatment being equal Ti being equal to 0, so conditional on being in the control condition. And you can already see that basically this is kind of a hypothetical or non-observed outcome. We're talking about the potential outcome in the treatment group for observations conditional on being in the control group. But this potential outcome in expectation is equal to the potential outcome in again in the treatment group, conditional on Ti being equal to 1. Okay, so that means since the potential outcomes yi1 and yi0 are independent of the treatment assignment, we can say that the expectation of the potential outcome for the treated observations, or the treatment potential outcome is equal across both the treatment group, across the control group and the treatment group, and that is equal to just the overall average of yi1. So it's the overall average of the potential outcomes under the treatment. So in our example, all the states that received or that implemented a minimum wage increase, the expectation of those potential outcomes, hypothetically, if all states increased the minimum wage, is, in the hypothetical sense, is equal in the treatment group as well as in the actual control group, right? So there's no systematic bias between states who received the treatment, so who increased the minimum wage, and who didn't receive the treatment, so who didn't increase the minimum wage, okay? And equivalently, we can say the same thing about the potential outcomes of the control. So the potential outcomes under the absence of the treatment is also equal, both conditional on the treatment assignment being equal to 0 and the treatment assignment being equal to 1. So again, conceptually, what this means is that the expectation of the potential outcomes, whether they're observed or not observed, as, hypothetically, we could think about it as if we were able to observe all potential outcomes. There's no systematic difference between the treatment group and the control group in terms of the potential outcomes. What would have happened had all the states not received the treatment, essentially. Okay. So if this is the case, if the potential outcomes are independent of treatment assignment, then we can express the average treatment effect as the expectation of yi1 in the treatment for all conditional on the treatment assignment being equal to 1 minus the expectation of yi0 conditional on the treatment assignment being equal to 0. Okay, so if you try to wrap your head around what is going on in these equations, ultimately, I think I want to go back to the table from the previous video, where we talked about the fundamental problem of causal inference, and where we basically said, okay, there are a lot of unobserved, a lot of question marks, a lot of unobserved potential outcomes, right? And ultimately, what we were saying by saying that the potential outcomes are independent of the treatment assignment, what we're saying is that we can basically, instead of looking at the overall, instead of looking at the average of all the observed and unobserved potential outcomes in the treatment and in the control, we can basically, in the treatment group, only rely on the observed realizations of the potential outcomes in the treatment group. So the y1s that we actually observe, and compare those to the potential outcome, the realized potential outcomes in the control group that we actually observe. Okay, so basically, what this assumption means is, if the treatment is independent of the potential outcomes, we can just rely on the observations that we actually, the realized potential outcomes that we actually observe. Okay. And that's why randomization is so important, because ultimately it allows us to overcome this problem, this fundamental problem of causal inference, by saying, if the treatment is independent of the potential outcomes, we can just use the potential outcomes that we observed, that were realized, to estimate the treatment effect that previously we defined based on a comparison between a factual and a counterfactual that we weren't actually able to observe, right? So that's actually that's actually a pretty cool thing. There are a couple of crucial assumptions for causal inference, and I just want to point out three really important ones that we see in the literature quite frequently. The first one is ignorability. Ignorability implies, and kind of what I discussed earlier, that the treatment assignments are statistically independent of the subject's potential outcomes. And it can be violated, or its violation can ultimately induce what is often called selection bias. Okay. In general, ignorability is guaranteed with random assignment, right? So this is one really important feature of random assignment, right? With random assignment, just to be clear, with random assignments, the treatments are allocated such that all units have some known probability between 0 and 1 of being placed in the treatment group, right? So it doesn't have to be equal probabilities, but it has to be some known probability, okay? When we talk about simple random assignment, what we mean is that basically, or complete random assignment, what we mean is that basically every condition has the same probability, but that doesn't have to be the case, okay? But the important thing is that with random assignment, these treatment assignments are by design statistically independent of the subject's potential outcomes. And ultimately that's what we describe by the treatment assignment is ignorable, or it satisfies the ignorability assumption. Okay, so why does violating this assumption induce selection bias? Okay, and here's one way to kind of mathematically show, or kind of give you a kind of conceptual idea of what we mean by selection bias. Okay, so we begin here with this basic conceptualization or definition of the average treatment effect that we had previously. So the expectation of the potential outcomes in the treatment group minus the expectation of the potential outcomes in the control group. That's the average treatment effect of our intervention. And so this difference we can expand a little, and basically we're just applying a little trick. And what I'm doing is I'm subtracting and adding the same term to this to this equation. So here in the first term is still the expectation of the potential outcome in the treatment group. At the end here, we still have the expectation of the potential outcome in the control group. But what we subtract and add is the expectation of the potential outcome in the control group conditional on the treatment assignment being equal to 1. Right? We subtract this and we add this. Okay. If we do this, we can then rearrange things a little bit. Specifically, we can group two things together. One is the difference between treatment and control conditional on treatment assignment being equal to 1. And this is this term up here. This is basically just taking this part, the original expectation of the potential outcome in the in the treatment, and we add this second part that we added. Okay, so that's now the difference, and this difference between yi1 and yi0 conditional on treatment status being equal to 1, or treatment assignment being equal to 1. That's what we call the average treatment effect among the treated. Okay, so it's the average. You can think about this as the treatment effect among everyone who actually received the treatment. Okay. And then we're left with the remaining two terms, which is one, the expectation of the potential outcomes in the treatment group, for those observations conditional on the treatment assignment being equal to 1, and the expectation of the potential outcome of the control group conditional on the treatment assignment being equal to 0. So conditional on being in the control group, right? And this difference, if this difference is not equal to 0, if this term does not cancel out, so in other words, if there's a systematic difference in the potential outcome of the control group, or the potential outcome in the control, conditional on the treatment assignment being equal to 1 and the treatment assignment being equal to 0, if there's a systematic bias in those two, that's ultimately what we talk about when we mean selection bias, right? So kind of look at those formula and kind of try to go through the logic, because ultimately what we see here is that the selection bias is basically a difference in the potential outcome between observations that were assigned to the treatment and observations that were assigned to the control. But it's a difference in the potential outcome if both of those groups, or both of those observations or groups of observations had actually been assigned to the control condition, right? So bringing this back to our example, what does this mean? This means that states that in our example of this minimum wage and unemployment, this means that selection bias occurs if states that implemented the minimum wage had a higher or lower baseline in unemployment than states that didn't implement the minimum wage. Okay. Another important assumption is excludability. The excludability assumption describes that the potential outcomes respond only to the receipt of the treatment, not to the random assignment of the treatment or any indirect byproduct of random assignment. So it is violated, for example, if different procedures are used to measure outcomes in the treatment and control groups, and or if research activities, other treatments, or third-party interventions other than the treatment of interest differentially affect the treatment and control groups. Okay, so this ultimately means that this is violated. Excludability is violated if something else is going on that is not directly part of the treatment, but that still affects the outcome that we're interested in. Okay. And then lastly, we have the non-interference assumption, which is sometimes abbreviated with SUTVA, stable unit treatment value assumption. And this assumption describes that potential outcomes of observation I reflect only the treatment or control status of observation I and not the other observations. So this is violated when subjects are aware of the treatments that other subjects receive, for example, or that treatments may be transmitted from treated to untreated subjects, or for example, if resources used to treat one set of subjects diminish resources that would otherwise be available to other subjects. Okay, so for example, if you think about a think about a lab experiment where you give people a survey and there are different conditions and people ultimately receive different surveys, but everyone is filling out the survey and they're sitting next to each other and they see what the other person's survey looks like. That would be a violation of this SUTVA assumption in the context of a lab experiment, for example. Okay. Now, in this step, I want to go through an example, but we're actually already quite long in this video. So what I'm going to do is I'm going to take a quick break, and in the next video, I will talk about a specific example from the book, which is the social pressure experiment examining the effect of social pressure on turnout and voting.